Welcome to Slumbertainment. Get comfortable, close your eyes, and let yourself relax. Tonight we explore the history of smithing. Please like and subscribe for more restful content. Now, let's begin. Before the first furnaces glowed in the dark of prehistory, before the hammer struck hot metal and sang its clear ringing tone, humankind lived within the quiet patience of stone. For hundreds of thousands of years, tools were chipped and shaped, not forged. The world was built from what the earth already offered: flint, bone, wood, and obsidian. Yet something within the human mind was restless, observant, drawn to change. In time, someone noticed that certain stones behaved differently when placed in fire. They did not crack or splinter, they softened, they shimmered. From that realization, the art of smithing began to emerge, a slow dawn of transformation that would carry human civilization from darkness into a new age of light and metal. The first steps toward metallurgy likely began with the discovery of native metals, small pieces of copper, gold, or meteoric iron found pure in nature. Unlike stone, these materials could be hammered into new shapes without shattering. Early peoples used simple pounding stones to flatten and fold soft metals, creating ornaments, small blades, or hooks. Gold, which gleamed brightly even after years in the earth, became the first metal of fascination. It was pliable, inert, and beautiful, qualities that made it ideal for early experimentation. Copper followed, more common but more reactive, and it was this reddish metal that first opened the true path towards smelting and alloying. Archaeological evidence traces the origins of copper use to around 9,000 years ago in the Near East, particularly in regions that would later form parts of modern-day Turkey and Iran. The earliest copper objects were cold-hammered, beaten into shape from native copper nuggets. These artifacts, pins, small awls, beads, mark the beginning of humanity's tactile relationship with metal. Yet it was not until people learned to extract copper from ore that true smithing began. This leap required fire, patience, and a growing understanding of how matter behaves under heat. Smelting was a remarkable discovery. At its core, it is the controlled reduction of metal ores using heat and a reducing agent, usually charcoal. In the prehistoric world, this was not a theoretical process, but an act of empirical curiosity. Ancient metallurgists noticed that stones containing copper would change colour when placed in a hot fire. The green or blue surface of malachite would darken, then yield small beads of glowing metal as the charcoal's carbon bonded with the oxygen in the ore. The resulting metallic droplets could be collected and hammered into usable forms. This discovery was nothing less than revolutionary. For the first time, humanity learned to transform the very fabric of the earth through deliberate chemical change. As copper became more common, smiths began to notice its limitations. Pure copper is soft. It dulls and bends easily. Somewhere in Mesopotamia or Anatolia, perhaps by accident, a smith introduced tin-bearing ore into a copper smelt. The result was bronze, harder, sharper, and more durable. Bronze ushered in a new age of craftsmanship and warfare. From about 3000 BCE onward, the Bronze Age spread across the ancient world, from the river valleys of Mesopotamia to the shores of the Mediterranean, across Europe and into China. The technology moved not only through trade, but through shared curiosity, carried by travellers who observed and experimented, spreading knowledge of fire and metal wherever they went. The first smiths were more than craftsmen. They were engineers, chemists and mystics, working with forces few fully understood. To transform ore into metal required temperatures beyond a normal wood fire. Bellows and furnaces were invented to feed air into the flames, raising heat to over 1,000 degrees Celsius. These devices, Simple leather bags or ceramic tubes became essential extensions of human breath, focusing energy and giving life to the forge. The smith's workspace evolved into something elemental, a meeting point between fire, air, earth, and water. Each component was vital. The fire melted the ore, the air fueled the flame. The earth provided both the raw materials and the clay to shape crucibles. Water cooled and tempered the finished work. This balance of forces gave smithing its enduring symbolism in human culture, a craft both practical and spiritual. Across early civilizations, metalworking became a mark of sophistication. In Sumer and Egypt, smiths were among the most respected artisans, often working under temple patronage or royal commission. The Egyptians, for example, revered the metalworker as one who imitated the creative power of their gods. Bronze tools built the pyramids, carved the stone temples, and shaped the jewelry that adorned the pharaohs. Every object carried within it the memory of fire, the silent witness to countless hours of heat, sweat, and precision. In Europe and the Aegean, the craft spread along trade networks that link the Minoans, Mycenaeans, and later the Greeks. Each culture refined the technology, improving furnace design and the composition of alloys. Meanwhile, in the Indus Valley and ancient China, independent traditions of metallurgy were developing in parallel. Chinese bronze casting achieved extraordinary sophistication by 1500 BCE, with complex ritual vessels produced using intricate clay molds. These pieces combined technical mastery with aesthetic grace, showing that smithing was not only a utilitarian skill, but also an art form that expressed cultural values and spiritual beliefs. Over centuries, the rhythm of the forge became embedded in the human experience. The slow heat of the coals, the hiss of quenching metal, the measured beat of the hammer, all formed a language of transformation. Smithing taught patience and respect for process. A smith could not rush the metal. Each stage demanded time and awareness. This quiet discipline fostered a reflective quality that endures even today. To watch a smith at work is to see focus embodied, a steady, deliberate conversation between mind and material. As societies expanded, so did their dependence on metal. Bronze tools made agriculture more efficient, allowing communities to cultivate larger fields and support growing populations. Weapons of bronze reshaped power structures, giving rise to organized armies and fortified cities. With these developments came new forms of trade, taxation, and governance. The forge, though small and humble, lay at the foundation of entire civilizations. Each hammerstroke echoed far beyond the workshop, influencing the structure of human life. Eventually, though, bronze reached its limits. Tin, an essential component of the alloy, was rare. Trade routes stretched far to obtain it, making production unstable. Around 1200 BCE, a series of disruptions known as the Bronze Age collapse rippled across the ancient world. Empires fell, cities burned, and with them much of the old knowledge faded. Yet from that destruction, a new discovery emerged: iron. Unlike copper or tin, iron ore was abundant, scattered across the continents in great deposits. But smelting it required even greater heat and skill. The transition would not happen overnight. It would take centuries of experimentation and adaptation. Still, the foundations had been laid. The mastery of metal, first born in the glowing crucibles of early copper smelters, would soon carry humanity into a new era. For now, though, the Bronze Age remains a symbol of balance between softness and strength, beauty and function, earth and fire. The first smiths, anonymous and forgotten, built not only tools, but the beginnings of scientific thought. They asked questions about cause and effect, about how heat could change matter, about why some stones yielded metal while others did not. These questions, simple yet profound, connected craft to curiosity. In every gleaming blade and cast vessel, one can sense the ancient wonder of discovery, the realization that the world could be transformed by knowledge. As night falls across the imagined landscape of prehistory, one can picture the faint glow of a furnace deep in a valley. Around it, figures move in rhythmic silence. Sparks rise into the air, bright against the dark. The sound of hammering drifts softly through the stillness, measured and unhurried. Each stroke shapes more than metal. It shapes the future. And as the embers fade, the story of smithing continues, quiet and enduring, waiting for the next dawn of fire. When the Bronze Age waned, the story of metal entered its next and most transformative chapter, the coming of iron. Unlike the scattered deposits of copper and tin, iron ore lay hidden in abundance beneath the soil of nearly every region on Earth. Yet this abundance was deceptive. To release the metal trapped within the iron oxides of hematite or magnetite required far greater heat than any copper furnace could provide. The earliest smiths who experimented with such ores would have found them stubborn and unyielding, their stone-like masses refusing to melt, but persistence, guided by the memory of fire, revealed a new secret. When heated long enough within a charcoal-rich atmosphere, the oxygen within the ore would bond with carbon, freeing iron in a spongy, semi-solid state. This bloom of metallic iron marked the birth of the Iron Age. The first evidence of deliberate iron smelting appears around 1500 BCE, possibly in Anatolia, though isolated examples occur earlier. These early smelters did not yet produce molten metal. Instead, the process yielded what is now called bloomery iron, a porous, slag-filled mass that had to be repeatedly heated and hammered to remove impurities. The result was wrought iron, tough and flexible, a material that could be shaped into weapons and tools of remarkable resilience. The transition from bronze to iron was not immediate, but once mastered, the new technology spread swiftly. Iron's strength, availability, and versatility reshaped human civilization more completely than any metal before it. In the Near East, the Hittites were among the first to control iron production at scale. Their skill granted them military and economic power, though for centuries iron remained rare and costly, valued almost as highly as gold. As techniques improved, particularly in controlling furnace temperature and air, iron became more common. The process was slow but inevitable. By 1200 BCE, ironworking had reached the Aegean and Egypt. Within several centuries, it had spread through Europe, India, and China, each region developing its own methods and traditions. Iron demanded a new kind of forge. The bloomery furnace, often built of clay or stone, stood as a small tower fed by charcoal and oxygen through bellows. Within its heat, chemistry performed its unseen work. Carbon from the charcoal removed oxygen from the ore, producing metallic iron and carbon monoxide gas. The molten waste, slag, separated and dripped away. The remaining bloom, glowing and heavy, was drawn from the furnace and hammered while still hot, each blow expelling trapped slag and consolidating the metal's grain. It was laborious, but it yielded a substance both tough and ductile, capable of enduring shock and strain in ways bronze could not. The craft of ironworking soon revealed a new dimension: carbon control. When iron absorbed small amounts of carbon during smelting or forging, its properties changed dramatically. Low-carbon iron was soft and malleable, while higher carbon content produced steel, harder and capable of taking a sharper edge. Ancient smiths may not have known the atomic reasons, but they observed the effects through countless cycles of trial and refinement. They learned to judge the metal by colour, by spark, by sound. the mastery of heat and timing became almost instinctive, and knowledge passed through demonstration rather than words. In ancient India, the production of high-quality steel emerged early. The crucible process used to make Wootz steel, documented as early as 300 BCE, achieved remarkable purity and strength. Iron and charcoal were sealed within small clay crucibles and heated until the metal absorbed carbon uniformly. The resulting ingots, once forged and polished, displayed distinctive patterns of light and dark bands, an early form of what would later be called Damascus steel. These steels were prized across Asia and the Middle East, valued for their resilience, sharpness, and almost organic beauty. Blades made from such metal seem to embody a living strength, flowing and flexible, yet unyielding. Meanwhile, in China, iron technology advanced along a different path. By the first millennium BCE, Chinese smelters had discovered how to reach higher temperatures using large blast furnaces and piston bellows. These could fully melt iron, producing cast iron that was hard but brittle. Through reheating and decarburization, they learned to convert it back into malleable wrought iron or steel. This cyclical process, smelting, casting, refining, represented a level of industrial organization far ahead of most contemporaries. Iron tools and ploughshares transformed agriculture. Iron nails, fittings, and weapons strengthened construction and defense. Metallurgy in China became both an art and a state science, recorded and regulated with precision. Across Europe, the blacksmith's forge became the center of community life. Unlike the centralized bronze foundries of earlier ages, ironwork could be practiced almost anywhere that ore and fuel were available. The village smith stood as a solitary craftsman, maintaining tools, repairing implements, and shaping objects that sustained daily existence. His forge glowed through long winters, its rhythmic hammering echoing across valleys. To many, the smith embodied mastery over nature itself, the one who could bend earth and fire to human purpose. Legends and mythologies reflected this reverence: the Greek Hephaestus, the Norse Wayland, the Celtic Goibniu, each a divine smith shaping the world through craft and flame. Technological progress accompanied this mythic reverence. By Roman times, iron was the foundation of empire. Roman engineers built vast networks of roads, aqueducts, and fortifications, all dependent on iron tools and fastenings. Their legions marched with iron weapons, their ships bound with iron nails. Archaeological remains reveal smelting sites throughout the provinces, evidence of organized, large-scale production. The process was standardized: ore roasted to remove moisture, charcoal produced in managed forests, furnaces constructed near water sources to drive bellows or hammers. This efficiency supported expansion, trade, and control. In the quiet rhythm of the forge, one can hear the machinery of empire at work. Yet even as iron empowered, it demanded constant care. Exposure to air and moisture caused rust, an inevitable corrosion that turned strength to fragility. Smiths learned to combat it through oiling, burnishing, and alloying. Small amounts of phosphorus or silicon could improve corrosion resistance. Quenching in oil or water could harden the surface. Through such refinements, iron became a living material, responsive, temperamental, requiring balance. Each piece carried within it the memory of its making, its unique pattern of heat and stress. This individuality gave rise to deep respect for the craft. No two blades were identical. No two bars behaved the same under the hammer. The forge was a place of observation as much as labour. As centuries passed, the knowledge of iron spread across continents. In Africa, skilled smiths of the Nok, Meroitic, and later West African cultures developed their own furnaces and techniques, independent of Eurasian influence. Archaeological finds show mastery of smelting and forging equal to any contemporary society. The craft held spiritual meaning, with smiths often occupying high social status. In many traditions, the act of smelting was accompanied by ritual, invoking balance between human effort and natural force. This interplay between technology and belief, between science and symbolism, is a recurring rhythm throughout the history of metallurgy. By the early medieval period, the blacksmith had become indispensable. From ploughshares to swords, from horseshoes to locks, the forge produced everything that bound communities together. Each spark from the anvil was part of a larger continuum of invention, a quiet dialogue between matter and mind. The age of iron was no longer an experiment. It was the foundation upon which societies rested, and within the steady pulse of hammer and flame, humanity had found not only strength, but rhythm, a mechanical heartbeat that would carry into the ages of steel and industry to come. As the night deepens, one can imagine the glow of a village forge centuries ago. The air smells of charcoal and metal. A smith bends over his anvil, the coals breathing beneath his bellows. The iron is soft, alive with heat. He lifts his hammer, strikes and listens. Each impact is a note in the long, slow symphony of progress, a sound that links him to those first fires of copper and to every forge that will follow. The mastery of iron laid the groundwork for a quieter but profound evolution, the refinement of steel. Where wrought iron had given humanity resilience, steel would bring precision. It was not a single invention but a gradual awakening, an understanding that the secret lay not merely in the ore but in the control of carbon. Every forge became a small laboratory where temperature, atmosphere, and time were balanced to alter the structure of metal. Each smith learned through touch and sound how to guide that transformation, how to make iron harder, sharper, more enduring. In the centuries following the fall of Rome, metallurgy did not vanish. It adapted. Across Europe, Asia, and Africa, small forges carried on the quiet continuity of skill. Villages depended on local smiths for tools, hinges, and weapons. In monasteries, scholars recorded techniques for tempering and hardening. The early medieval period saw the slow reorganization of knowledge, fragmented, empirical, but never lost. Iron and steel were part of daily survival, and even as empires shifted, the forge remained constant. In that constancy, metallurgy became a bridge between generations, an unbroken chain of practical wisdom. The process of making steel was still more art than science. The carbon content of iron determined its hardness, but control was elusive. Too little, and the metal bent. Too much, and it shattered. The only tools available to the smith were heat, colour, and sound. The colour of heated metal, red, orange, yellow, white, became a language. Experienced eyes could read temperature within a few degrees. The quenching process, plunging hot metal into water or oil, was equally delicate. It locked carbon into the iron's structure, creating martensite, the phase responsible for hardness. But if the cooling was too rapid, cracks formed. Thus, tempering followed, reheating the hardened piece to a gentler glow, allowing internal stresses to relax. This interplay of hardening and softening mirrored the rhythms of nature itself: contraction and expansion, tension and release. Throughout Eurasia, variations of this process produced distinctive metallurgical traditions. In Japan, the craft of sword making reached unmatched refinement. Tamahagani steel, smelted from iron sand in clay furnaces called tatara, was folded repeatedly to remove impurities and distribute carbon evenly. The resulting blades balanced strength and flexibility, a harmony of internal structure achieved through patience and precision. To modernize, The samurai sword became a symbol, but in truth, it was the culmination of deep metallurgical intuition, a synthesis of material science and ritual discipline centuries before either term existed. In the Islamic world, the reputation of Damascus steel grew legendary. Originating from Wootz ingots imported from India, these blades were forged in workshops from Persia to Syria. Their surfaces shimmered with organic, watery patterns, evidence of microstructures now known as carbide bands. These patterns were not mere decoration, but signs of strength. The blades could hold an edge while remaining flexible, properties that mystified European smiths for centuries. Only much later would metallurgists, using microscopes and chemistry, understand the crystalline reasons behind that beauty. While Asia and the Middle East refined elegance, Europe's metallurgical progress turned towards scale and application. The Carolingian and later medieval periods saw the growth of bloomery complexes capable of producing tons of wrought iron annually. Water wheels powered bellows, automating air supply and raising furnace temperatures more consistently. In the forests of Germany, Sweden and England, these forges became the industrial heart of early economies. The water-powered hammer, ancestor of the mechanical trip hammer, multiplied human effort, turning the rhythmic blows of one smith into the ceaseless work of many. By the High Middle Ages, blacksmithing had diversified into specialized trades: armorers, bladesmiths, farriers, and nailmakers. Guilds formed to regulate training and maintain quality. Their oaths, tools, and secrets created a shared culture of craftsmanship. Apprentices learned to prepare charcoal, to test ores, to judge a forge's draft by the movement of flame. Though their terminology was local, their practice was universal, an empirical science before the age of formal chemistry. Every hammer strike, every failed casting, was a data point in the long experiment of civilization. The development of the blast furnace marked a new threshold. Emerging in China centuries earlier and reaching Europe by the 13th century, this innovation allowed complete melting of iron, producing cast iron directly from ore. It was brittle but abundant. The ability to pour molten metal into molds revolutionized production. Cannons, bells, stoves, and architectural fittings became possible at unprecedented scale. The blast furnace also foreshadowed the industrial world to come, a continuous process rather than a single act of craftsmanship. The smith's forge had always been intimate, human, slow. The furnace introduced continuity, heat without rest, production without pause. Cast iron's hardness came at the cost of ductility, but metallurgists soon learned to convert it into malleable forms by decarburization, reheating in oxidizing environments to reduce carbon content. This technique bridged the gap between wrought iron and cast iron, leading toward modern steelmaking. Each advance rested on empirical understanding, and the men who worked the furnaces did not speak in terms of carbon atoms or phase transitions. They spoke of sweet or cold metal, of heat that was alive or dead. These words, grounded in physical observation, were the vocabulary of a pre-scientific but deeply intelligent tradition. In the Islamic Golden Age, scholars such as Al-Kindi and Al-Biruni documented the properties of metals, noting how different heats and quenching methods changed strength and colour. Their treatises formed the intellectual bridge between craft and theory. In Europe, the first systematic texts on metallurgy appeared in the Renaissance, notably De Re Metallica by Georgius Agricola in 1556. His careful descriptions of mining, smelting, and refining captured a world on the edge of transformation, a craft becoming a science. The blacksmith's intuition was about to meet the language of chemistry. Through all these centuries, the forge remained both workplace and sanctuary. The smell of coal and the hiss of water on hot metal carried through villages, comforting in their constancy. The smith's tools, anvil, tongs, bellows, hardly changed for millennia, yet each embodied accumulated knowledge. In the darkness of the forge, illuminated only by firelight, the boundary between ancient and modern blurred. Whether in medieval Europe or Tokugawa Japan, the rhythm was the same: fire breathing, hammer falling, metal yielding. Progress was slow but steady, guided by repetition and reflection. By the time the Renaissance unfolded, the world's knowledge of metallurgy had grown vast but fragmented. Every region had mastered part of the puzzle. China the furnace, India the steel, Europe the mechanism. Soon these threads would intertwine, and the smith's art would evolve into the engineer's science. The quiet forges of the medieval world would give way to roaring mills, yet the essence of the craft, transforming earth with heat and intention, would remain unchanged. In the stillness of evening, one can imagine a medieval smith closing his forge for the night. The coals dim, the air cools, and the last glow fades from the anvil's face. Around him lie the tools of generations past, worn but enduring. Tomorrow the fire will be lit again, the iron will soften, and the long conversation between humanity and metal will continue, steady, luminous, and endless. The Renaissance marked a turning point in the long dialogue between humans and metal. The world was waking to measurement, to repeatable experiment, to the idea that nature could be understood as system rather than mystery. Smithing, once the guarded art of guilds and hermits, began to merge with observation and written knowledge. For the first time, the secrets of the forge were being documented not only for apprentices, but for scholars. The blacksmith's craft was stepping into the light of science. In the 15th and 16th centuries, metallurgy and mining rose together as engines of European progress. Silver and copper fueled new economies, while iron built their ships and weapons. The furnace became not just a workshop, but a symbol of civilization's reach into the earth. Towns formed around mines and forges. Forests were managed to sustain charcoal production. Rivers were diverted to power bellows and hammers. The rhythm of the hammer on the anvil echoed the rhythm of empire expanding. The sounds of metal and progress became inseparable. It was within this world that Georgius Agricola published De Re Metallica in 1556. His book, illustrated with meticulous woodcuts, described every stage of mining, smelting, and metal refinement then known. It was not poetry but precision. Measurements, instruments, and processes set down as if to freeze centuries of craft into method. Agricola treated metallurgy as an organized field, not a collection of mysteries. He measured furnace temperatures by color, classified ores by behavior, and described the physical layout of smelteries in almost mathematical detail. His work stood at the boundary of two worlds, one still ruled by experience, the other by systematic inquiry. The Renaissance also deepened the philosophical meaning of transformation. Alchemists, often dismissed as dreamers, played a subtle role in this evolution. While their pursuit of transmutation from base metals to gold may seem fanciful, their experiments taught the methods of heating, distillation, and observation. The laboratory of alchemy was a parallel forge, and though its goals were metaphysical, its outcomes were technical. Many early metallurgists learned from alchemists how to control reactions and record observations. In their crucibles and retorts, metal was not only matter but metaphor, representing change, purification, and the promise of understanding. As trade expanded across continents, the knowledge of metal flowed with it. Spanish and Portuguese explorers carried European ironwork to the Americas, encountering indigenous metallurgies already rich with their own traditions. In the Andes, the Inca and earlier cultures had mastered cold hammering and casting of gold, silver, and copper alloys, creating intricate works that balanced utility and ritual beauty. Though their societies lacked large-scale iron smelting, their skill in controlling metal surfaces and colours was remarkable. When European furnaces met these New World artisans, two distinct metallurgical lineages briefly intertwined before conquest disrupted them. The global story of metal widened, though not always peacefully. By the 17th century, metallurgy was maturing into a recognizable science. Theories of combustion and air, though incomplete, began to move beyond superstition. The rise of chemistry gave smiths and scholars alike a new vocabulary. The discovery that air played a role in oxidation and that carbon could change metal properties transformed what had been instinct into hypothesis. Experiment replaced tradition as the highest authority. Yet even as furnaces grew larger and instruments more precise, the forge itself retained its ancient intimacy. The smith still read his metal by glow and tone. The scientific lens widened, but the human touch remained central. In Europe's northern forests, particularly in Sweden and England, iron production scaled upward. Water-powered blast furnaces, tall and narrow, reached operating temperatures high enough to produce molten iron continuously. This was the foundation of cast iron manufacture, supplying both domestic goods and the infrastructure of modernity. Ploughshares, pots, cannon, and anchors. The quality of ore mattered greatly. Swedish mines like those at Dannemora and Norrberg provided exceptionally pure magnetite, producing iron of such reliability that it became a European standard. The metal from these sources would later feed the first experiments in high-quality steel production during the Industrial Age. Smithing, however, remained personal. Even as furnaces multiplied, individual blacksmiths continued to serve as the bridge between raw material and use. In villages, the forge was the centre of repair, adaptation, and invention. Iron implements arrived from distant foundries, but it was the local smith who gave them function, reshaping, sharpening, reforging. The continuity of craft persisted beneath the rising machinery of progress. The glow of a rural forge, faint against the night, still represented the same ancient ritual of transformation. At the same time, artisans and scientists began to intersect more directly. In England, Robert Boyle's work on gases led to clearer understanding of combustion and oxidation. In Germany, experiments in heat and metal expansion hinted at the behaviour of atoms long before atomic theory. These shifts were slow but irreversible. The forge was no longer a purely practical domain. It was entering the realm of quantifiable science. The very elements that the smith manipulated with instinct would soon be measured, named, and classified. Iron, once seen as a divine gift of the earth, would be recognized as a combination of protons and electrons, structured in predictable lattices, an understanding unimaginable to the first smelters of copper millennia before. Still, amid this growing precision, the craft retained its meditative rhythm. To watch a smith in the Renaissance was to see an unbroken lineage stretching back to the first fires of Anatolia. The same gestures persisted, tongs gripping the glowing metal, hammer rising and falling with slow certainty, the hiss of quenching water filling the air. Each act repeated ancient knowledge that words could never capture. The hammer was both instrument and teacher, translating heat into structure, effort into permanence. The metals themselves were changing too. New alloys emerged, brass from copper and zinc, pewter from tin and lead, and new grades of steel from refined carbon control. The discovery of zinc in the late 16th century made brass production more consistent, giving rise to instruments, navigational tools, and decorative fittings that defined the aesthetic of the age. Gunmetal, an alloy of bronze optimized for artillery, embodied the intersection of craft and conflict, marking a world that now wielded metallurgy not just for survival but for expansion. In Asia, metallurgical innovation continued along parallel lines. In India, Wootz steel remained a coveted export, while in Japan, swordsmiths like Masamune refined tamahagami into blades of near-mythic quality. In China, iron production sustained immense agricultural networks, with blast furnaces centuries ahead of Europe's early designs. Though continents apart, these traditions shared the same fundamental dialogue, the effort to balance heat, carbon, and purity. Whether by intuition or calculation, the physics of transformation was universal. By the dawn of the 18th century, the world stood at the threshold of industrial transformation. The craft of smithing, rooted in repetition and patience, was about to feed into processes that multiplied its scale beyond imagination. Water wheels would soon drive more than bellows. They would turn hammers, presses, and eventually rolling mills. Charcoal would give way to coke, and furnaces would grow tall enough to cast whole bridges and engines. Yet this industrial horizon still rested upon the timeless foundation of the smith's art, the understanding that metal, under heat and pressure, reveals both its weakness and its strength. In the final quiet hours of a Renaissance forge, one could still hear the same elemental symphony that had played for 10,000 years. The fire breathes, the hammer strikes, the metal yields and cools, hardening into form. The world outside is changing. Printing presses, telescopes, and machines are being born. But within the forge, time slows. The glow of the coals flickers against stone walls, and in that light, past and future converge. The smith, anonymous yet eternal, continues the ancient work of shaping the earth into meaning. The 18th century marked the beginning of a new rhythm in the long story of metal, a rhythm of industry. The quiet, cyclic labour of individual forges began to merge into the continuous pulse of mechanical production. What had been the art of a craftsman working by firelight became, step by step, the foundation of an industrial age that would remake landscapes, cities, and societies. Metallurgy, once guided by instinct and touch, was entering an age of scale, precision, and relentless innovation. The key to this transformation was heat. Charcoal, the traditional fuel of smelting, was pure but limited. It required vast forests to sustain, and as Europe's hunger for iron grew, deforestation became a constraint. The furnaces of Sweden, Germany, and England consumed wood faster than it could regrow. The solution came from below the earth: coal. For centuries it had been known, but it burned with impurities that tainted iron. Then, in the early 1700s, a breakthrough, Abraham Darby of Coalbrookdale, discovered how to use coke, a refined form of coal, as a clean, high-temperature fuel for blast furnaces. Coke-fired iron-making broke the link between forests and furnaces. It was the opening move of the Industrial Revolution. Darby's process changed everything. Coke allowed furnaces to burn hotter and longer, producing large volumes of cast iron with unprecedented consistency. For the first time, iron became a mass-produced material rather than a local craft. Its uses multiplied: bridges, rails, cylinders, gears, and pipes. What had once been shaped by hand could now be poured in tons. The old bloomery, where a smith extracted small lumps of wrought iron through patient hammering, gave way to the roaring blast furnace, tall, hot, and unceasing. The sound of the hammer was replaced by the deep roar of combustion and the hiss of molten metal meeting air. This abundance reshaped society. Iron became the skeleton of modernity. It carried water through pipes, spanned rivers with bridges, and turned the wheels of new machines. The steam engine, perfected by James Watt in the late 18th century, owed its life to improved iron. Its cylinders demanded precision casting and strong, heat-resistant material. Iron fed the engine, and the engine fed industry. Coal mines deepened, furnaces multiplied, and metallurgy expanded from craft into infrastructure. The forge had become a system. Amid this scale, new metallurgical questions arose. Cast iron was abundant but brittle. Wrought iron was tough but labour-intensive. Steel, the perfect intermediate, remained expensive and rare. Traditional methods such as cementation, heating wrought iron in charcoal for days to allow carbon diffusion, produced limited quantities. The challenge was not understanding steel, but producing it efficiently. In the early industrial world, that challenge drove invention like a magnet pulling iron filings into order. Henry Cort's puddling process, introduced in the 1780s, represented a bridge between eras. In a reverberatory furnace, where the fuel was separated from the iron by flame, molten pig iron could be stirred or puddled to remove carbon and impurities. The result was refined wrought iron produced at scale, malleable yet strong. This process powered the great works of the 19th century, bridges, ships and railways, while keeping alive the tactile presence of the smith. Though now aided by machines, the puddler's task remained physical, judging metal by glow and fluidity, reading its behaviour like an ancient craftsman. As iron became the heart of civilization, metallurgy turned scientific. The chemistry of oxidation, reduction, and carbon content began to be measured, not just observed. Antoine Lavoisier's work on combustion clarified the role of oxygen. John Dalton's atomic theory gave structure to matter itself. Metallurgy shifted from empirical art to applied science. Experiments in crystallography revealed that metals were not homogeneous, but composed of ordered lattices, structures that explained hardness, elasticity, and fatigue. For the first time, smiths and scientists were speaking a shared language, though they stood in different worlds. The industrial forge changed human experience of sound, light, and labour. Where once a single hammer beat in rhythm with a man's breath, now hundreds of tons of metal moved in unison under steam-powered hammers. Joseph Nasmyth's invention of the steam hammer in the 1840s symbolised this transition perfectly. It could forge ship anchors and locomotive parts, its blows precise and adjustable, its power immense. Yet the principle remained the same: heat, impact, transformation. The scale had expanded, but the essence was unchanged. Across the Atlantic, the United States embraced iron as the language of growth. Railroads, bridges, and machinery demanded consistent, strong metal. Foundries rose along rivers, where water and coal were abundant. The smell of soot and molten slag became the scent of progress. In this world of mass production, the blacksmith still survived, tending to the needs of towns and farms. But he now worked beside machines that echoed his rhythm with mechanical precision. The old forge was being absorbed into the larger organism of industry. Even as furnaces roared, the art of metallurgy deepened in scientific detail. The phenomenon of tempering and phase change was examined under microscopes. Henry Clifton Sorby's pioneering metallographic studies in the mid-19th century revealed the microstructure of steel, showing for the first time that the material's behaviour was rooted in the geometry of crystals. The once mystical art of hardening now had visible proof: microscopic networks of ferrite, pearlite, and martensite. The ancient intuition of the smith, knowing that colour and timing shaped strength, had found its scientific explanation. Meanwhile, new alloys expanded the range of human capability. The addition of nickel, chromium, and manganese produced steels of superior toughness and corrosion resistance. brass and bronze evolved into specialized materials for instruments, bearings, and architecture. The idea of alloying, deliberately combining metals to tailor their properties, was the quiet revolution beneath the louder one of machines. Metallurgy was becoming design, a way to engineer behavior at the atomic level long before the word engineering took on its modern sense. The aesthetic of iron began to shape architecture. Wrought iron railings, cast iron facades, and great structural arches appeared across cities. The Crystal Palace, built for London's Great Exhibition of 1851, stood as a monument to iron's new identity. Transparent, ordered, and immense. The material that once lived only in forges and battlefields now framed glass walls for art and science. Iron had become both skeleton and skin, a medium of structure and beauty. Yet this expansion brought tension. The smoke of furnaces darkened skies. The clang of progress drowned quiet landscapes. For the first time, humanity's mastery of metal began to reshape not just its tools, but the environment itself. The same fire that once liberated copper from stone now burned on continental scale, consuming coal, consuming time. The glow of the forge had spread across nations, its light both creative and consuming. Still, in the midst of the machine age, the human relationship with metal remained intimate. In every foundry, workers stood before heat that demanded respect. They read molten surfaces for signs of readiness, moved with deliberate rhythm, and knew instinctively when metal was alive and when it was dead. This continuity of attention, this calm, physical intelligence, was what connected the ancient smelter in Anatolia to the industrial worker of Birmingham or Pittsburgh. The tools had changed, but the gaze and patience were the same. By the end of the 18th century and into the 19th, iron and steel had become inseparable from progress itself. Nations measured their strength in tonnage. Bridges spanned miles. Ships crossed oceans, and machines transformed labour. Yet in the quiet of a forge, whether industrial or rural, the same soft glow persisted. The glow of transformation, of matter yielding to will. The history of smithing had entered its loudest age, but at its core it remained the same silent dialogue between fire and form, between human intention and the patient, unyielding nature of metal. The 19th century became the age of steel. For thousands of years, humanity had known it in small, precious quantities. Hard to make, harder to control. But now, through chemistry, engineering, and relentless experimentation, steel would cease to be rare. It would become the backbone of industry, empire, and architecture. The transition from iron to steel was not sudden. It was a chain reaction of insight, each discovery refining the next, until the entire world was remade in alloy and flame. The pivot point was the Bessemer process. In 1856, Henry Bessemer, an English inventor, introduced a method that transformed molten pig iron into steel by blowing air through it. The principle was simple but powerful. The oxygen in the air combined with the carbon and silicon impurities in the iron, burning them away and releasing intense heat. The result was molten steel, produced in minutes instead of days. This single idea reduced cost, increased scale, and altered history. What had once required careful handwork and patient judgment could now be done by measured air and time. Bessemer's converter, a vast pear-shaped vessel lined with refractory clay, stood as a new kind of furnace, part laboratory, part engine. The roar of the air blast, the white arc of molten metal, and the sudden quiet as impurities burned out, all became the sounds and sights of modernity. Steel poured from these furnaces built railways, ships, and weapons. It was strong, cheap, and infinitely reproducible. The age of craft had yielded to the age of process. Yet Bessemer's breakthrough was not perfect. his method struggled with certain ores, particularly those high in phosphorus. It took another innovation, the basic oxygen process, developed later from the work of Sidney Gilchrist Thomas. To solve this, by using a basic refractory lining, phosphorus could be removed efficiently, broadening the range of usable ores. This refinement made steel truly global, no longer limited by geography. Where iron existed, industry could rise. Almost in parallel, William Siemens developed the open hearth furnace, capable of precise temperature control through the regenerative use of exhaust heat. The open hearth process was slower, but offered exact control over composition. By adjusting carbon and alloying elements, metallurgists could tailor steel for specific uses: rails, armor plate, tools, or wire. This was the dawn of metallurgical engineering, steel as a designed material, not a simple metal. By the late 19th century, the open hearth furnace dominated steelmaking across Europe and America. Its orange glow lit entire skylines, turning night into day above the foundries of Sheffield, Essen, and Pittsburgh. Steel transformed the physical world. It built railways that stitched continents together. It raised bridges like the Forth and Brooklyn, suspended on cables of spun steel that defied wind and water. It framed skyscrapers that reached skyward, redefining what cities could be. The Eiffel Tower, completed in 1889, stood as both monument and proof, a statement of what metallurgical mastery could achieve. Beneath its elegant lines lay the logic of carbon, iron, and heat perfectly balanced. Industry itself took on the logic of metallurgy: continuous flow, controlled reaction, efficiency from chaos. The blacksmith's forge had become the integrated steelworks, an ecosystem of blast furnaces, converters, and rolling mills operating as one. The rhythm of hammer and anvil was replaced by the deep mechanical pulse of pistons, presses, and cranes. Workers no longer shaped individual tools. They tended to systems that produced millions. The intimacy of touch gave way to the precision of instruments, yet both relied on the same understanding: that metal was alive to temperature, that its strength was earned by fire. Beneath the surface, science was catching up with practice. The new discipline of materials science began to map the inner world of metals. Microscopy revealed grain structures, dislocations, and the crystalline phases that determined hardness and ductility. The iron-carbon phase diagram, first outlined in the late 1800s, became a kind of map of transformation, showing how temperature and composition shaped structure. Metallurgy was no longer mystery, it was physics in motion. The smith's instincts now had equations. In this same period, alloy steels emerged. By adding elements such as nickel, chromium, vanadium, and tungsten, engineers could produce steels that resisted corrosion, retained strength at high temperatures, or cut through other metals. These were the materials of the new age: turbine blades, armor plate, precision tools, and later, stainless steel. In 1913, Harry Brearley of Sheffield discovered that adding chromium to steel created a surface resistant to rust. The result was stainless steel, a metal of clarity and permanence, soon to be used in everything from surgical instruments to skyscraper facades. It symbolized the scientific maturity of metallurgy, control not just of heat but of chemistry itself. The industrial forge became global. Steelworks rose in Russia, Japan, and the United States, each adapted to local conditions but united by method. Rivers carried ore, ships brought coal, railways carried the finished metal back to the world. Every nation measured progress in tons of output. The air over the industrial districts glowed red through the night, the colour of ambition and exhaustion combined. The world was being rebuilt in its own reflection, structured and strong, but increasingly mechanical. Amid the noise of foundries and the expansion of cities, the ancient symbolism of the smith persisted. Workers still spoke of born metal and dead metal, of good heat and bad draw, of temper and soul. These words echoed older times but carried practical meaning. Even in the most advanced plant, experience remained vital. Machines could not replace the eye that judged colour, the hand that knew when a pour was ready. Metallurgy was becoming science, but it was still craft at heart, a discipline of awareness as much as precision. Steel also reshaped the human relationship with time. Before the Industrial Revolution, metalworking followed seasonal and social rhythms, harvests, daylight, and community. In the Steel Age, the furnace could not rest. Once ignited, it ran for years, consuming air and fuel without pause. Labour became shift work, divided by hours instead of seasons. The forge's heartbeat was now mechanical, indifferent to sunrise or sunset. Yet the sight of molten steel pouring from a ladle remained mesmerising. Light made tangible, energy flowing in visible form. By the turn of the 20th century, the mastery of steel had set the stage for modern civilization. It supported railways, ships, bridges, and the skeletons of cities. It carried electricity, powered engines, and built weapons that could reshape nations. Humanity had learned to command the elements with confidence, but also at cost. The earth yielded ore, the air thickened with smoke, and fire no longer symbolized mystery. It symbolized control. Still, in every bright furnace, one could sense continuity. The same ore, the same patience, the same act of shaping chaos into order. As the century closed, metallurgy stood on the threshold of the modern scientific age. The forge, once ruled by instinct, now operated through thermodynamics, crystallography, and chemistry. But beneath the equations, the craft endured. The act of forging remained as it had always been, a dialogue between resistance and intention, between the human will and the deep, slow logic of matter. In that enduring rhythm, the story of smithing carried forward, unbroken, from the ancient hammer to the mechanized mill, from glowing bloom to molten steel. By the early 20th century, metallurgy had entered a phase of precision and scale that previous centuries could not have imagined. Steel was no longer a symbol of progress, it was its foundation. From railways and bridges to machines, tools and weapons, the world ran on alloy and combustion. Yet even as mass production expanded, the scientific understanding of metals deepened in quiet laboratories far from the roar of the furnaces. Smithing, now redefined as material science and industrial metallurgy, began to turn inward, toward the atomic and crystalline structures that governed all its mysteries. The language of metallurgy changed. Where once a smith spoke of colour, spark and texture, engineers now spoke of grain boundaries, dislocations, and phase equilibria. The iron-carbon system became a kind of sacred chart, showing how temperature and composition governed transformations between ferrite, austenite, and cementite. The blacksmith's instinctive quenching was now described in terms of time-temperature transformation curves, diagrams mapping how steel hardened or softened depending on heat and time. The forge had become a laboratory, and intuition had found its mirror in mathematics. In the years leading to the First World War, steelmaking reached industrial maturity. The open hearth process still dominated, but electric furnaces were beginning to appear. These offered even greater control of purity and temperature, powered not by coal but by current. The electric arc furnace, developed by Paul Herold in 1907, allowed small batches of specialty steel to be melted with precision. Alloy steels, tool steels and stainless steels all demanded the fine control that electricity could provide. The furnace, once a symbol of brute energy, had become an instrument of accuracy. The relationship between metallurgy and warfare deepened during this era. Every advance in material strength or hardness translated directly into military potential. The great battleships of the early 1900s were floating demonstrations of metallurgical progress, hulls and armor plates designed through chemistry, not intuition. The same was true of artillery, whose barrels demanded steels that could resist repeated explosive stresses. The First World War accelerated all of this. To sustain it, nations turned their entire economies into foundries, with steel production as the measure of endurance. The forge had become national. Yet amid this industrial violence, the craft element of smithing persisted. The maintenance of weapons, engines, and tools still required skilled metal workers who could weld, temper, and repair by hand. The traditional skills of heating, quenching, and shaping, though now supported by science, remained indispensable. A broken engine part in a battlefield workshop might be repaired by a man who understood the same principles as a medieval swordsmith, judging heat by colour, hardness by sound, and temper by touch. Technology advanced, but the human connection to metal endured. After the war, metallurgists sought to understand why metals behaved as they did under stress. Theories of crystal defects, particularly dislocations, emerged from the work of Taylor, Orowan, and Polanyi in the 1930s. They showed that the plastic deformation of metals, their ability to bend without breaking, was not random, but the result of tiny imperfections moving through crystal lattices. Strength, it turned out, came from controlling these imperfections. This insight transformed metallurgy from chemistry into physics, from process into structure. It explained why forging improved metal, the mechanical working of hot steel refined grains and distributed dislocations, producing toughness through microscopic order. The Second World War brought metallurgy to new extremes. Lightweight alloys became vital for aircraft and vehicles. Aluminum, once rare, was produced in vast quantities through electrolysis. Magnesium and titanium joined it as strategic materials. The race for stronger, lighter, and more heat-resistant metals was intense. Jet engines demanded alloys that could withstand temperatures beyond those any previous furnace had reached. Out of this came the nickel-based superalloys, Inconel, Hastelloy, and their kin, designed not by craft, but by calculation. The blacksmith's fire had evolved into the controlled heat of turbines and reactors. In civilian life, metallurgy was transforming modern comfort. Stainless steel moved from laboratories into kitchens, hospitals, and architecture. Its clean, reflective surface became a symbol of hygiene and progress. Aluminum, malleable and bright, became the metal of modernity, used in airplanes, automobiles, and everyday objects. The properties that ancient smiths had once discovered through intuition, ductility, workability, and corrosion resistance, were now precisely measured and manipulated. Metal had become democratic, its refinement woven into the fabric of daily life. In the mid-20th century, the field of metallurgy split into two complementary paths: physical metallurgy and extractive metallurgy. One dealt with the behaviour and microstructure of metals, the other with their recovery from ore. Extractive metallurgy itself had changed completely since the charcoal furnaces of the past. Ore was now treated chemically through flotation, leaching and reduction before smelting. Electric furnaces and continuous casting systems replaced the batch processes of earlier centuries. The same principle endured, purification by heat and reaction, but now executed with industrial precision and global scale. The emergence of the metallurgical microscope, and later the electron microscope, allowed scientists to observe metal structure in ways that would once have seemed impossible. Grain boundaries, inclusions, and phase transformations could now be seen directly, revealing the inner geometry of strength. Every fracture, every pattern of wear could be traced to microstructure. The smith's ancient belief that metal possessed character or temper found its rational foundation in crystal science. Each alloy was indeed alive in its own way, responsive, structured, and dynamic under stress. By the 1950s, metallurgy had become inseparable from the modern world's ambitions. Nuclear reactors, spacecraft, and supersonic jets depended on materials that could survive extremes of heat, radiation, and pressure. New alloys were designed atom by atom, with precise control of composition and microstructure. Powder metallurgy emerged as a method for producing components with near-perfect uniformity. Metal powders pressed and sintered into solid forms without melting. Forging itself evolved into high-pressure, isothermal processes, where temperature and strain were mathematically controlled. The act of shaping metal was now guided by sensors and formulas, but its essence, heat, pressure, transformation, remained unchanged. Amid all this innovation, the memory of traditional smithing persisted as a kind of cultural anchor. Blacksmiths still worked in small forges across the world, creating tools, art, and hardware by hand. The old methods, drawing, upsetting, folding, tempering, were now practiced as heritage rather than necessity, yet they retained their quiet precision. The forge had become symbolic, a reminder that progress began with fire, that every modern machine carried within it the ghost of hammer and anvil. The continuity between the artisan and the engineer was not broken, only transformed in scale and understanding. By the late 20th century, metallurgy was no longer confined to metals alone. Its principles extended to ceramics, polymers, and composites, any material whose structure and performance could be shaped through heat and stress. Yet the roots of it all lay in smithing, the control of phase change, the reading of colour and texture, the mastery of transformation. The ancient furnace and the modern reactor both operated on the same truth, that all matter responds to energy, and that form is a function of how that energy is applied. In every laboratory and factory, the slow patience of the smith still resonated. Whether measured in centuries or seconds, metallurgy remained a conversation between humanity and the material world, a balance between intention and resistance. The blacksmith's fire had become electricity, plasma, and laser, but the purpose was unchanged: to take what the earth offered and give it shape, strength, and purpose. The journey that began with stone and spark had entered the atomic age, yet its rhythm remained constant. The quiet hum of transformation, the steady pulse of metal under human will. As the 20th century progressed, metallurgy evolved into a discipline defined as much by experimentation and computation as by furnace and hammer. The post-war period accelerated this evolution, driven by the demands of aviation, space exploration, and nuclear power. The need for metals that could withstand extreme temperatures, stress, and corrosion led to entirely new categories of alloys. Traditional iron and steel remained central, but aluminum, titanium, and nickel-based superalloys became the materials of advanced engineering. Metallurgy had become predictive. The properties of a metal could be designed before it was ever poured, forged, or cast. Aerospace technology exemplified this shift. Jet engines required alloys that maintained structural integrity at temperatures exceeding 1000 degrees Celsius, far beyond the capabilities of ordinary steel. Nickel-based superalloys achieved this through carefully controlled microstructures and precise alloying. The addition of elements like chromium, cobalt, and molybdenum, combined with thermomechanical processing, created metals that retained strength while resisting creep and oxidation. Every component, from turbine blade to combustion chamber, was the product of calculation and iteration. modern metallurgy functioning as both art and applied science. Meanwhile, titanium emerged as a metal of exceptional promise. Lightweight, strong, and corrosion-resistant, it became critical for both aerospace and chemical applications. Unlike steel, titanium requires specialized furnaces to prevent contamination and maintain purity, and even minor impurities can drastically affect performance. Early production methods were labor-intensive, relying on the Kroll process to reduce titanium tetrachloride to metal. This metal, once rare and difficult to work, eventually became ubiquitous in aircraft frames, medical implants, and high-performance equipment. The metal that once could only be observed, folded, and tempered by hand was now understood in atomic terms, its behavior calculated before any heat was applied. The field of metallurgy also expanded into structural analysis and failure science. Engineers realized that the properties of a metal were not solely dependent on composition, but on the stresses and strains imposed throughout its life. Fatigue, fracture, and corrosion became measurable phenomena. The advent of high-speed photography, X-ray diffraction, and electron microscopy allowed researchers to observe dislocations moving through crystals, microcracks propagating under load, and corrosion mechanisms at interfaces. Metal was no longer mysterious. It was dynamic, responsive, and quantifiable. Yet the fundamental principle remained unchanged. Heat and stress shape matter. Industrial production also transformed. Continuous casting, introduced in the mid-20th century, replaced batch processes for steel, improving uniformity and efficiency. Rolling mills could shape steel into beams, rails, and sheets with remarkable precision, while computer-controlled furnaces maintained exact temperature profiles throughout. The forge had become a factory, yet the essential knowledge, the timing of heat, the influence of alloy, the importance of cooling, still echoed the intuition of ancient smiths. Modern engineers in effect extended the craft into a mechanized global system. Simultaneously, specialty alloys were developed for electronics, medicine, and energy systems. Copper alloys optimized for electrical conductivity, stainless steels for surgical instruments, and zirconium for nuclear reactors demonstrated metallurgy's reach into fields previously unimaginable. Material science became interdisciplinary, integrating physics, chemistry, and mechanical engineering. Yet despite the abstraction, the principles of heat treatment, phase transformation, and grain structure still governed performance. The smith's language had been translated into equations, but the ideas endured. Even as new metals emerged, iron and steel maintained their central role. Structural steels evolved with precise carbon content, controlled alloying, and thermomechanical processing to meet modern building codes. High-strength, low-alloy steels allowed for taller buildings and longer bridges, while tempered and quenched steels made vehicles lighter and safer. The industrial scale enabled consistent properties across thousands of tons of material, yet the underlying metallurgical principles remained timeless. Grain size, carbon content, and controlled cooling dictated hardness, ductility, and toughness. Education and research expanded in parallel. Universities and laboratories established dedicated departments of metallurgy and material science, formalizing knowledge that had been empirical for millennia. Metallurgists became scientists and engineers, trained to analyze, predict, and optimize. Laboratories reproduced ancient processes, comparing them to modern alloys to understand historical craftsmanship. In some cases, the patterns in Damascus steel or Japanese Tamahagani blades could now be quantified, explained, and replicated in modern labs, proof that even centuries-old craftsmanship had been informed by material science, albeit instinctively. By the mid-20th century, metallurgy had become global in scale and scope. International collaboration accelerated the exchange of techniques, standards, and research. Countries competed not only in production, but in the development of superior alloys for aerospace, defense, and energy. Metallurgy had grown from a village craft to a strategic national capability. Yet through all this, the fundamental story remained: the transformation of raw metal through heat, force, and knowledge. The forge had multiplied, but the dialogue between human intention and material response was unchanged. Even as computers began to simulate alloy behavior and laser technologies allowed for micro-welding and additive manufacturing, the connection to ancient smithing persisted. Heat, pressure, and chemistry still governed outcomes. The modern metallurgist, whether in a clean room or beside a blast furnace, continued the same practice as the smith of Anatolia or the blacksmith of medieval Europe, observing, controlling, and shaping metal to purpose. The methods had evolved, but the essential relationship between human skill and the responsiveness of metal had endured across millennia, carrying the craft from spark-lit forges into the age of atoms and electrons. As the 20th century advanced, metallurgy moved beyond traditional metals into new frontiers, expanding both in scale and in conceptual understanding. Materials that were once exotic became routine, and alloys could be engineered with properties tailored for precise applications. Aerospace, electronics, medicine, and energy demanded metals that behaved predictably under extremes of heat, stress, and corrosion. The focus shifted from simply producing steel or iron to designing materials with defined microstructures and performance characteristics. In essence, the smith's ancient practice of observation, trial, and adjustment became a science capable of predictive control. One of the defining developments of this era was the rise of high-performance alloys. Nickel-based superalloys, for example, were designed to maintain strength at temperatures exceeding 1,000 degrees Celsius, making them indispensable for jet turbines and rocket engines. The arrangement of their crystals, the balance of alloying elements, and the precise thermal treatments applied during manufacturing determined whether a turbine blade would withstand continuous high-speed rotation or fail catastrophically. In this way, metallurgy had transformed from art into applied physics, yet the underlying principle remained constant. Heat and pressure shape the properties of metal. Aluminum also came into prominence as a material of lightness and corrosion resistance. Once rare and difficult to extract, it became widely available through electrolytic processes. Engineers learned to combine it with copper, magnesium, and silicon to create aircraft-grade alloys that were both strong and lightweight. Titanium followed a similar path, prized for its strength-to-weight ratio and resistance to oxidation. Both metals required careful handling and precise thermal control, echoing centuries of experience in smelting and forging, though executed now on industrial and atomic scales. In parallel, stainless steel revolutionized industries from medicine to architecture. Its resistance to corrosion and staining made it ideal for surgical instruments, food processing equipment, and building facades. Its creation depended on understanding how chromium content and carbon levels interact to form a passive oxide layer on the surface, a protective shield invisible to the naked eye. The smith's ancient intuition about temper and corrosion had evolved into a predictable, measurable property governed by chemistry and structure. The mid-20th century also saw the application of metallurgy to electronics and energy. Copper alloys optimized for electrical conductivity powered the rapidly expanding telecommunications infrastructure, while nickel and cobalt alloys found use in electric motors and generators. Nuclear energy demanded zirconium and stainless steel capable of withstanding radiation and high-temperature water. Metallurgy was no longer a background craft. It had become an essential enabler of technological civilization. The relationship between material and machine was as critical as that between human and tool. Simultaneously, the study of failure became a formal science. Engineers began analysing fatigue, creep, and fracture, recognising that even the strongest metals could fail under repeated or sustained stress. Microscopic examination revealed dislocations, inclusions, and other imperfections that influence performance. Understanding these phenomena allowed for the creation of more durable structures and safer machines. Once again, the lessons of the forge, attention to defects, careful handling of heat and gradual shaping, found their scientific expression in modern laboratories. The evolution of industrial processes continued. Continuous casting replaced older batch methods, improving efficiency and uniformity. Rolling mills and heat treatment facilities became highly automated, yet human oversight remained essential. Metallurgists monitored temperature, chemical composition, and microstructure, making adjustments in real time to ensure desired properties. The ancient skills of the smith, judging heat, reading the behavior of metal, and adjusting technique, had been translated into instrumentation, sensors, and computer control, but the principle remained unchanged. Careful attention to transformation produces reliable material. Additive manufacturing, or metal 3D printing, emerged as a new frontier in metallurgy. Using powdered metals fused by lasers or electron beams, engineers could produce components with complex geometries previously impossible to cast or machine. This method demanded detailed understanding of thermal gradients, solidification rates, and alloy behavior. Even in this advanced technology, the lineage of the forge was visible. Heat applied locally, layer by layer, shaped the material's structure and performance, echoing the ancient rhythms of hammer, fire, and cooling. Through all these developments, the conceptual continuity of metallurgy persisted. Whether in a Renaissance forge, a Bessemer converter, or a modern laboratory, the process relied on controlling energy, observing behavior, and understanding the material's response. Metals, once mysterious and temperamental, could now be designed, predicted, and optimized. Yet each step retained the ancient rhythm, transformation through heat and force, patience, and precise timing. The craft had evolved, but its fundamental principles had endured across millennia. In the quiet of laboratories, foundries, and workshops, one could still trace the long history of smithing. Sparks and flames might have been replaced by lasers and electric arcs, but the dialogue between human intention and metallic response remained. Grain structures, phases, and alloys were simply modern expressions of the same truths that ancient smiths observed in bloomery iron and wrought steel. The story of metallurgy, stretching from the first smelted copper to the advanced alloys of the 21st century, is a testament to humanity's enduring capacity to understand, shape, and coexist with the fundamental materials of the earth. The latter half of the 20th century introduced new dimensions to metallurgy, particularly through computational methods and advanced characterization techniques. Engineers could now model the behavior of metals before they were ever produced, predicting strength, fatigue resistance, and thermal tolerance. Finite element analysis allowed structures to be simulated under complex stress patterns, while phase diagrams and thermodynamic models enabled precise alloy design. What had once been guided by observation, trial, and empirical rules could now be optimized mathematically, yet the same fundamental laws of heat, pressure, and composition governed every outcome. Materials science extended beyond metals into composites and intermetallic compounds, blending principles of traditional metallurgy with modern engineering. High-performance alloys were combined with ceramics or polymers to create materials capable of extreme performance. Jet engines relied on nickel-based superalloys reinforced with ceramic coatings, achieving thermal resistance and structural stability far beyond earlier possibilities. Titanium matrix composites reduced weight while maintaining rigidity in aerospace applications. Even in these highly engineered systems, the foundational understanding of atomic structure, phase transformations, and thermal treatment trace directly to centuries of smithing knowledge. The evolution of steel continued with the development of microalloyed steels, high-strength low-alloy (HSLA) steels, and advanced high-strength steels (AHSS). These materials provided improved strength-to-weight ratios, enabling longer bridges, taller skyscrapers, and lighter vehicles. Precise control of carbon, nitrogen, and trace elements combined with thermal processing allowed engineers to design steels with exceptional toughness and ductility. The underlying principle, metal responding predictably to heat and composition, remained the constant bridge between craft and science. Industrial automation transformed production processes. Continuous casting and rolling were now supplemented by computer-controlled heat treatment, robotic handling, and real-time quality monitoring. Yet human oversight continued to play a critical role, especially in assessing surface quality, interpreting metallographic samples, and ensuring that theoretical predictions matched real-world performance. The dialogue between human skill and technological instrumentation mirrored the dialogue between ancient smith and metal. Experience still guided the application of power and heat. In nuclear applications, metallurgy reached unprecedented complexity. Zirconium alloys were chosen for fuel cladding due to their low neutron absorption and corrosion resistance. Reactor steels were developed to withstand both radiation-induced embrittlement and high-temperature water exposure. Every design decision depended on a microscopic understanding of phase stability, dislocation movement, and corrosion kinetics. The knowledge that the smith had once applied to judging quench temperature and temper now informed the construction of components critical to the global energy infrastructure. Additive manufacturing matured further, allowing intricate lattice structures to be built for aerospace and biomedical applications. Metals were processed layer by layer, with heat input carefully controlled to minimize residual stresses and defects. Powder metallurgy enabled the creation of components with tailored microstructures, including gradient alloys and functionally graded materials. The practice demanded a deep understanding of metallurgy, yet its principles were grounded in the same interplay of temperature, time, and composition that had guided smiths for millennia. The 21st century introduced extreme environments, from deep space missions to high-speed hypersonic vehicles. Metals and alloys had to endure temperatures and stresses previously unimaginable. Refractory metals, such as tungsten, molybdenum, and tantalum, were combined with advanced cooling methods and surface treatments to maintain integrity. Ceramics and composites were integrated, but metals continued to provide essential toughness and ductility. Even in these advanced systems, the principles of atomic structure, heat treatment, and phase transformation, observed in the simplest medieval forge, remained relevant. In everyday life, metallurgy's influence was equally pervasive yet subtle. Stainless steel, aluminum alloys, and precision-engineered copper conductors formed the backbone of infrastructure, transportation, and medical devices. Microstructure and composition dictated performance, durability, and longevity. Engineers relied on centuries of accumulated knowledge, augmented by modern science, to produce reliable and safe materials. The craft that once demanded intuition had evolved into a combination of prediction, analysis, and synthesis, yet its essence was unchanged. Through all these advances, one constant persisted: the human fascination with transformation. The smith's hammer may have been replaced by lasers and presses, but the rhythm of heat, force, and careful observation endured. Metallurgy remained a dialogue between intention and material, between human understanding and the fundamental properties of matter. The forge, whether ancient, industrial or modern, continued to symbolize humanity's enduring relationship with metal, a bond forged through millennia of observation, experimentation, and patient refinement. The story of metallurgy, from the first smelted copper to the most advanced alloys of the modern era, illustrates a continuity of purpose. To understand the Earth's materials and to shape them into tools, structures, and technologies that extend human capability. Across centuries, cultures, and technological revolutions, the principles of smithing, heat, pressure, and transformation have remained universal, linking past and present in an unbroken chain of knowledge and skill. In contemporary metallurgy, the boundaries of the field continue to expand. While traditional metals like steel, aluminum, and copper remain central, modern applications demand combinations of properties that cannot be achieved through simple alloying alone. High-entropy alloys composed of multiple principal elements in nearly equal proportions represent one such innovation. These materials exhibit exceptional strength, thermal stability, and corrosion resistance, properties that arise not from conventional balance of carbon and iron, but from complex atomic interactions. In essence, metallurgists now manipulate matter at a scale that once would have seemed abstract, yet the foundational principles, phase behavior, heat treatment, and microstructure, remain consistent with the observations of ancient smiths. Nanotechnology has introduced another layer of control. By manipulating metals at the nanometer scale, engineers can influence grain boundaries, dislocation densities, and surface energies in ways that dramatically alter performance. Coatings, surface modifications, and nanostructured alloys can improve wear resistance, reduce friction, and increase strength without increasing weight. These techniques are, in effect, an extension of traditional tempering and alloying, but executed with precision tools and instruments that allow observation and control far beyond human perception. Additive manufacturing has matured into an essential method for high-performance components. Selective laser melting and electron beam melting allow complex geometries to be fabricated directly from digital models. The layering process requires precise control of thermal gradients, cooling rates, and powder composition to avoid defects. The principles are reminiscent of forging. Heat, solidification, and mechanical behavior are intimately linked. Every modern laser or electron beam is a descendant of the simple forge fire, applying energy to metal to produce form and function. Modern metallurgy also emphasizes sustainability and resource efficiency. Recycling of metals reduces the demand for virgin ore, but requires careful understanding of impurity behavior and alloy compatibility. Electronic waste, rich in copper, gold, and rare metals, is processed using metallurgical techniques that recover high-purity materials. Even these processes rely on the same underlying principles that guided early smelters: controlled heating, chemical separation, and an understanding of material behavior under changing conditions. The craft of transformation, once localized and intimate, now operates on a global scale with environmental awareness as a guiding principle. Materials designed for energy applications illustrate the scale and precision of modern metallurgy. Turbine blades in power plants and jet engines must resist creep and oxidation at temperatures exceeding 1,200 degrees Celsius. Specialized alloys, often with protective coatings and graded microstructures, are designed to distribute stress, manage thermal expansion, and prevent corrosion. Understanding how dislocations move, how grains interact, and how alloying elements diffuse through a lattice is essential. These are the same principles that governed hammer and quench, now expressed through calculation, simulation, and advanced instrumentation. Biomedical applications extend metallurgy into intimate contact with human life. Implants, prosthetics, and surgical instruments rely on biocompatible metals such as titanium and cobalt chromium alloys. Surface treatments enhance osseointegration, wear resistance, and corrosion protection. These metals must be produced to strict microstructural standards to ensure predictable behavior under physiological conditions. The smith's ancient concern with temper and hardness has found its modern parallel in microscopic control of structure and performance for human safety and longevity. Even in electronics, metallurgy remains foundational. Copper and aluminum conductors, gold contacts, and solder alloys underpin global communication networks. Advances in microelectronics require precise control of thermal and mechanical properties at microscopic scales, with every thermal cycle influencing performance. The principles of heat flow, thermal expansion, and metallurgical phase changes remain central, echoing the insights gained over millennia. Education and research have become increasingly specialized. Materials science departments now integrate physics, chemistry, and engineering, focusing on predictive modeling, computational thermodynamics, and advanced characterization. Laboratories reproduce ancient alloys to study their microstructure and properties, comparing traditional methods to modern understanding. The continuity is remarkable. The behavior of metal under heat and stress, first observed by ancient smiths, can now be quantified, modeled, and optimized. Across all these developments, one enduring principle persists. Metals respond predictably to controlled energy input. Whether the medium is fire, coke, electricity, or laser, the law remains consistent. Heat, pressure, and alloying determine microstructure and performance. The modern metallurgist, like the ancient smith, interprets these signals, applies controlled transformation, and produces materials suited to purpose. The continuity between craft and science, between intuition and calculation, is unbroken. Thus, the story of metallurgy is both ancient and contemporary, spanning millennia of human observation, experimentation, and innovation. From the first smelted copper to the engineered alloys of the 21st century, the principles have remained. Controlled transformation produces strength, ductility, and utility. Every bridge, turbine, implant, or aircraft wing carries within it the legacy of countless generations of smiths and metallurgists, each building upon the knowledge of those who came before, transforming matter to meet human needs, and refining their understanding with every spark, hammer strike, and measured calculation. The 21st century continues to redefine the scope and ambition of metallurgy. Modern challenges demand materials that can perform in extreme environments while minimizing weight, energy consumption, and environmental impact. Aerospace, energy, medicine, and electronics place unprecedented demands on metals and alloys, driving innovation at scales both macroscopic and atomic. Despite this, the principles of transformation, heat, stress, composition, and microstructure remain the unifying foundation of the field. The work of ancient smiths is echoed in laboratories and factories, though amplified by technology and guided by rigorous science. Advanced computational tools now allow metallurgists to predict behavior before metals are ever processed. Finite element analysis, molecular dynamic simulations, and thermodynamic modeling provide insights into deformation, fatigue, and corrosion. Engineers can simulate millions of cycles of stress on a component, visualize atomic diffusion, or design alloys with specific phase distributions. Yet these calculations are grounded in the same laws of material response that ancient smiths observed empirically. Metals harden or soften under heat, yield under force, and respond to impurities in predictable ways. Human insight remains essential, translating numerical predictions into practical methods for production and processing. Additive manufacturing has become transformative for both research and production. Selective laser melting, electron beam melting, and direct energy deposition techniques allow metals to be built layer by layer, producing geometries that traditional forging or casting could never achieve. Each layer of powder, melted and solidified under controlled conditions, must maintain proper microstructure and mechanical properties. Thermal gradients, cooling rates, and residual stresses must all be managed carefully. This precision is reminiscent of the rhythmic observation in traditional smithing. The artisan judges the colour of heated metal or the sound of a hammer on steel, while the modern engineer interprets data from sensors and simulations. Metallurgy in energy applications has expanded to include materials for nuclear reactors, concentrated solar power, and high-efficiency turbines. Nickel-based superalloys, titanium alloys, and ceramic metal composites provide strength, corrosion resistance, and thermal stability. The internal structure of these metals, the arrangement of grains, dislocations, and phases, determines performance at extreme temperatures. Heat treatment and thermomechanical processing remain critical. What was once the judgment of the smith over a glowing bloom is now the control of furnaces, presses, and rolling systems guided by sensors and computer algorithms. Environmental concerns also influence metallurgy. Recycling and sustainable processing have become priorities, as raw metal extraction carries significant ecological costs. Advanced sorting, smelting, and purification methods allow metals to be recovered from industrial scrap and electronic waste. Understanding how impurities affect alloy behavior is essential for these processes, linking modern sustainability to the same principles that guided earlier smiths. Metals must be purified and transformed carefully to achieve predictable performance. Biomedical metallurgy illustrates the intimate human impact of material science. Titanium, cobalt chromium alloys, and stainless steels are engineered for implants, prosthetics, and surgical tools. Surface treatments enhance biocompatibility and wear resistance, while precise control of microstructure ensures predictable mechanical behavior. The smith's ancient concern for temper and ductility finds its modern equivalent in designing metals that can coexist with the human body for decades, performing reliably under dynamic, repetitive loads. Even electronics relies fundamentally on metallurgical principles. Copper, gold, and aluminum conductors, along with solder alloys, form the backbone of global communications. As electronic components shrink, thermal and mechanical stresses become increasingly significant. Understanding metallurgical behavior at the microscopic scale is essential to ensure reliability and longevity. Phase changes, diffusion, and residual stresses dictate performance, echoing the same principles that governed metalworking long before the advent of electricity. Education and research have become highly specialized, yet they maintain continuity with ancient practice. Metallurgists study historic techniques, replicate ancient alloys, and analyze artifacts to understand the relationship between structure and function. These studies reveal that intuition, observation, and hands-on experience guided the development of material knowledge for millennia. The modern engineer combines that historical understanding with computational prediction, experimental analysis, and precision processing. Across all these applications, one constant remains. Metals respond to controlled energy input in predictable ways. Heat, pressure, and composition determine strength, ductility, and performance. The modern metallurgist, like the smith of antiquity, observes, interprets, warps, and applies controlled transformations to achieve desired outcomes. The dialogue between human skill and material behavior is unbroken, even as tools, techniques, and scales evolve. The history of metallurgy, spanning from the first smelted copper to today's engineered alloys and composites, illustrates an enduring human pursuit, the understanding and shaping of the materials that make civilization possible. Every structure, machine and device embodies centuries of knowledge, each layer of microstructure a reflection of observation, experimentation, and refinement. Through fire, furnace, and modern laboratory, the transformation of matter remains both a practical endeavour and a timeless narrative of human ingenuity. In the contemporary era, metallurgy has grown increasingly interdisciplinary, merging with physics, chemistry, computational modelling, and even biology. Materials are no longer understood solely by their chemical composition or the shape of grains under a microscope. They are analysed at the atomic and molecular levels. Techniques such as electron microscopy, X-ray diffraction, and atom probe tomography allow scientists to observe the arrangement of individual atoms, the distribution of alloying elements, and the progression of defects with unprecedented precision. These observations inform the design of metals for extreme performance, bridging the gap between ancient craft and modern science. High-performance alloys have become central to aerospace, energy, and defense. Nickel-based superalloys remain critical for turbine engines, where thermal and mechanical stresses are extreme. Titanium alloys, lightweight yet strong, are used in aircraft frames, medical implants, and spacecraft. Advanced steel grades, including dual-phase and trip, transformation-induced plasticity, steels, provide high strength and ductility for automotive and structural applications. Each alloy is carefully designed, balancing composition, heat treatment, and mechanical processing to achieve the desired properties. The same attention to detail that guided the medieval smith in judging heat and hammer strikes now informs processes controlled by computer and sensor networks. Additive manufacturing continues to expand the possibilities of metallurgy. Layered construction allows intricate geometries and internal structures previously impossible to produce. This process demands precise control over thermal cycles, cooling rates, and powder composition. Microstructure and mechanical properties are influenced by each laser pass, each layer solidified. In effect, additive manufacturing is a modern extension of forging and welding, replacing hammers and anvils with beams of energy while maintaining the fundamental principles of heat, transformation, and stress. Sustainability has become a central concern in modern metallurgy. Recycling metals from industrial scrap and electronic waste requires an understanding of phase behavior, impurity control, and alloy compatibility. For example, recovered aluminum or copper must be refined and adjusted to maintain performance standards. Metallurgists now balance environmental responsibility with the traditional goals of strength, durability, and manufacturability. In this way, the ancient craft of extracting and refining metals has been adapted to address the ecological challenges of a global civilization. Biomedical applications illustrate the intimate human impact of metallurgical science. Implants, prosthetics, and surgical tools rely on metals engineered for long-term performance within the body. Titanium and cobalt chromium alloys are optimized for strength, biocompatibility, and corrosion resistance. Surface treatments encourage integration with bone or tissue, while careful control of microstructure ensures predictable mechanical response. The smith's concern with temper, hardness, and ductility finds a modern parallel in ensuring that metals perform reliably under repeated biological and mechanical loads. Electronics and energy storage present additional challenges. Conductors, contacts, and battery components require precise thermal and mechanical properties. Phase stability, conductivity, and corrosion resistance dictate performance and longevity. Advances in metallurgical science, including nanoscale structuring and surface modification, allow materials to meet the demands of high-speed computing, telecommunications, and renewable energy systems. Once again, the basic principles of controlled transformation, alloying, and thermal treatment guide the creation of reliable materials. Education and research integrate computational modeling with empirical experimentation. Material scientists simulate microstructure evolution, phase transformations, and mechanical behavior using advanced software, while verifying predictions through laboratory analysis. Historical techniques, such as traditional forging and tempering, are still studied to understand the principles underlying material behavior. This synthesis of past and present ensures that the centuries of accumulated metallurgical knowledge remain relevant and accessible. Throughout all these developments, one enduring principle persists. Metals respond predictably to energy input, whether from heat, pressure, or mechanical deformation. Control of this response allows humanity to shape metals to purpose, from the earliest smelted copper to today's high-performance alloys and composites. The dialogue between human skill and material behavior, begun in ancient forges, continues through laboratories, factories, and workshops worldwide. The story of metallurgy is thus both a record of technological progress and a testament to enduring principles. From fire-lit bloomery forges to modern additive manufacturing and alloy design, the transformation of matter under human intention remains central. Every bridge, aircraft, implant, and electronic device carries within it the legacy of countless smiths and metallurgists, their accumulated knowledge shaping civilization in tangible, enduring ways. Through millennia, the principles of heat, stress, and microstructure have remained constants, guiding humanity in its quest to understand and manipulate the materials of the earth. As metallurgy continues into the 21st century, its scope encompasses not only strength and durability, but also adaptability, sustainability, and precision at microscopic and atomic scales. Modern engineers and scientists consider how metals interact with their environments, how they age over decades, and how they can be optimized for both performance and ecological responsibility. Heat, pressure, composition, and microstructure remain the foundational variables, yet their application is now informed by advanced modeling, experimental observation, and decades of accumulated knowledge. The dialogue between human intention and material response is unchanged, even as the tools and scales evolve. High-performance alloys dominate aerospace and defense applications. Nickel-based superalloys maintain structural integrity in turbine engines at temperatures exceeding 1,000 degrees Celsius. Titanium alloys combine lightness with strength for aircraft frames, spacecraft, and medical implants. Advanced steels, including dual-phase and transformation-induced plasticity steels, provide high strength and ductility in automotive, structural, and industrial applications. In each case, microstructure, phase distribution, and impurity control are carefully designed. Ancient smiths judged metal behavior by color and sound. Modern engineers observe electron microscopy images and thermal gradients. Yet the fundamental principle, material responding predictably to energy input, remains the same. Additive manufacturing has revolutionized both research and production. Layered construction allows complex geometries and internal lattice structures, impossible to achieve with traditional forging or casting. Each laser or electron beam melts successive layers of powder with precise thermal control, influencing microstructure and mechanical properties. Thermal gradients, cooling rates, and residual stresses are carefully monitored. The process is a modern echo of forging and welding, replacing hammers and anvils with energy beams while maintaining the essential principles of heat, transformation, and stress. Sustainability shapes modern metallurgy. Metals are increasingly recycled from industrial scrap and electronic waste, demanding an understanding of phase behavior, impurity control, and alloy compatibility. Refined metals must meet precise composition and microstructure standards to retain performance. The ancient craft of extracting and purifying metals has been adapted to a global scale with environmental awareness, showing that the transformation of metal has always required both skill and foresight. Biomedical applications highlight metallurgy's intimate connection with human life. Titanium and cobalt-chromium alloys are optimized for implants and prosthetics, providing biocompatibility, corrosion resistance, and mechanical reliability. Surface treatments enhance integration with bone or tissue, while microstructural control ensures predictable performance under repeated stress. The smith's concern with temper, hardness, and ductility finds a modern expression in designing metals to function within the human body, enduring forces and time with reliability. In electronics and energy, metallurgical principles continue to underpin performance. Copper, aluminum, and specialized alloys conduct electricity with minimal resistance. Microstructure, phase stability, and surface characteristics govern reliability, durability, and efficiency. Nanostructured coatings and alloys reduce wear, prevent corrosion, and manage thermal effects. The ancient practice of observing and responding to material behavior persists, translated now into microscopic and atomic scale precision. Education and research increasingly combine computation with empirical observation. Simulations of microstructure evolution, phase transformations, and mechanical behavior guide experimental design. Laboratory studies validate predictions and refine understanding. Historical techniques, such as forging and traditional heat treatment, are studied to illuminate underlying material principles. This integration ensures that centuries of accumulated knowledge remain relevant, informing innovation in modern materials science. Throughout these advances, one constant persists. Metals respond predictably to controlled energy input. Whether in ancient bloomery forges, industrial foundries, or modern additive manufacturing labs, heat, pressure, and composition govern strength, ductility, and corrosion resistance. Human skill interprets these responses, guiding transformation and shaping matter to purpose. The lineage from early smiths to contemporary metallurgists is unbroken, spanning millennia of observation, experimentation, and refinement. The story of metallurgy, stretching from the first smelted copper to advanced modern alloys, is a record of continuity and evolution. Each generation of smiths and metallurgists has expanded human understanding of metals, translating intuition into theory, trial into technology. Every bridge, vehicle, implant, or electronic device embodies this legacy, a tangible testament to the principles of heat, stress, and microstructure that have governed metals for thousands of years. Across time, the dialogue between humanity and metal remains central to civilization, reflecting both mastery and understanding of the materials that shape the world. The narrative of metallurgy reaches a remarkable convergence in the 21st century, where ancient craft and modern science coexist seamlessly. The same principles observed by early smiths, heat, pressure, composition, and transformation, continue to guide the creation of materials, yet they are applied with precision, scale, and analytical rigor unimaginable in earlier eras. Metals are no longer simply shaped by intuition. They are designed atom by atom, layer by layer, for specific performance under extreme conditions. Despite technological advancement, the enduring theme remains: understanding matter and guiding its behavior to meet human needs. High-performance alloys dominate advanced engineering, from aerospace to energy to medicine. Nickel-based superalloys endure extreme heat in jet and rocket engines, while titanium alloys combine lightness with strength in aircraft, spacecraft, and biomedical implants. Advanced steels, engineered with precise microstructures and alloying, provide both strength and ductility in automotive, structural, and industrial applications. These materials are the culmination of centuries of observation, experimentation, and refinement. The principles that guided the hand of the medieval smith, judging heat by colour, assessing temper by sound, have evolved into digital modelling, microstructural analysis, and thermal simulations, yet they remain conceptually identical. Additive manufacturing exemplifies the continuity of the craft. Powdered metals are fused layer by layer using lasers or electron beams, building components impossible to produce by traditional forging or casting. Each layer must solidify with the correct microstructure, mechanical properties, and thermal history. Residual stresses are carefully monitored and defects minimized. The process mirrors ancient forging in its rhythm. Controlled application of energy to shape, refine, and strengthen metal. The tools have changed, but the fundamental human engagement with material transformation persists. Sustainability and resource efficiency have become integral to metallurgy. Recycling and reclaiming metals from industrial scrap and electronic waste requires an understanding of phase behavior, impurity control, and alloy compatibility. Engineers refine materials to meet strict composition and performance standards, echoing the ancient practice of purifying and tempering metals to achieve predictable properties. Environmental stewardship has become a modern extension of the timeless principle. Careful control of material transformation ensures utility, reliability, and longevity. Biomedical metallurgy emphasizes the intimate relationship between metals and human life. Titanium, cobalt, chromium, and stainless steel alloys are engineered for implants, prosthetics, and surgical tools. Surface treatments enhance biocompatibility, while precise microstructural control ensures predictable mechanical response under repeated physiological loads. The smith's concern with temper, ductility, and hardness finds contemporary expression in designing metals that endure inside the human body, performing reliably over decades. Even in electronics, metallurgical principles remain foundational. Copper, aluminum, gold, and specialized alloys provide the backbone of global communication and energy systems. Microstructure, phase stability, and surface properties govern conductivity, reliability, and longevity. Nanostructured coatings and alloys reduce wear, prevent corrosion, and manage thermal stresses. The ancient practice of observing and responding to material behavior persists, now applied at microscopic and atomic scales. Education and research integrate computational modeling, experimentation, and historical knowledge. Simulations of microstructure evolution, phase transformation, and mechanical behavior guide design, while laboratory validation refines understanding. Historical techniques are studied to illuminate the principles underlying material behavior, ensuring continuity between centuries of practice and modern innovation. The lineage from early smiths to contemporary metallurgists remains unbroken, a testament to the enduring human pursuit of mastery over matter. Throughout the evolution of metallurgy, one principle remains constant. Metals respond predictably to controlled energy input. Whether in a charcoal-fueled bloomery, a mechanized steel mill, or a modern additive manufacturing lab, heat, pressure, and composition dictate strength, ductility, and corrosion resistance. Human skill interprets these responses, guiding transformation to achieve desired outcomes. The dialogue between human intention and material behavior, begun in the earliest forges, continues to shape civilization. The story of metallurgy, spanning from the first smelted copper to advanced alloys and engineered composites, is a testament to human ingenuity, persistence, and observation. Every bridge, aircraft, implant, or electronic device carries within it the accumulated knowledge of generations of smiths and metallurgists. Across millennia, the principles of heat, stress, microstructure, and transformation have remained central, linking ancient craft to modern science. In every application, metals continue to respond to human guidance, shaping the world and reflecting the enduring interplay between knowledge, skill, and the fundamental properties of matter.